In this video, we'll look at the binary search algorithm. We'll see how it works and briefly compare it to the linear search algorithm. We'll see that the binary search algorithm is a lot more efficient than the linear search. The binary search algorithm is a commonly used and easily understood algorithm, which makes it a useful example for learning to study algorithm performance. Suppose you are on a long and boring car trip with a younger relative, for example, your nephew, Timmy. You offer to play a number guessing game with him. You say, "I'll pick a number between 1 and 10, inclusive," and you try to guess it. For each guess you make, I'll tell you if the guess is correct, or whether you should guess higher or lower. Timmy, who is just starting grade school, asks you what inclusive means, and you tell him that 1 and 10 are allowed in the game. You also have the foresight to say that only whole numbers are allowed, not fractions like 1.5. So Timmy agrees to play. You say, "Okay, I've got a number." Timmy guesses 1. You say, "Higher." Timmy guesses 2. You say, "Higher." Timmy guesses 3. You say, "Higher." Timmy guesses 4. Let's stop here and analyze Timmy's algorithm. It appears that Timmy is using what's called a linear search. Start at one end of the list and proceed through each of the items in order. If you play this game several times while randomly picking numbers, the best that the guesser can hope for is that he or she guesses it on the first attempt. The worst situation is that the guesser will have to go all the way through the list before finding the number. The average number of guesses to find the correct number will be approximately 5, or perhaps 5.5. Now, also riding in the car is your niece, Dawn. She's several years older and smarter than the nephew. She says, "I can guess the number quicker than Timmy can." You believe her, so you say that you'll pick numbers between 1 and 100 inclusive, and again, no fractions are allowed. Then you pick a number, let's say 8. Dawn guesses 50. You say lower. She guesses 25. You say lower. She guesses 12. You say lower. She guesses 6. You say higher. She says, let's see, halfway between 6 and 12 is 9. Is it 9? You say lower. She says, halfway between 6 and 9 is either 7 or 8. Is it 7? You say higher. She says, then it must be 8. She turns to Timmy and says, "What I was doing was picking the middle number in the list of possibilities. If I guess the number, great. If I'm told the number is lower, I pick halfway through the lower half of the remaining possibilities. If I'm told the guess is higher, I guess halfway through the upper half of remaining possibilities." You say, "You're pretty bright, Dawn." The algorithm that Dawn used is called the binary search. It's called binary because with each guess, the algorithm divides the list in half. Let's analyze the performance of the binary search algorithm. The best case occurs when the guesser guesses the number on the first attempt. What's the worst case? The answer to that is the same as, what is the maximum number of times that you can divide the list in half before you reach only one possibility? Then guess that remaining number. It turns out that for 100 consecutive numbers, the maximum number of guesses you would need is 7. Sometimes you'll get lucky and guess it in 5 or 6 guesses, but the worst case is 7. In fact, we could have played this game with the values 1 through 128 and gotten the same results. We can divide 128 in half 7 times until we get down to the number that must be the answer. If we divide it in half, we get a list of at most 64. Divide it in half again, we get a list of at most 32 numbers. Divide it in half again, at most 16 numbers. In half again, 8. and half again 4, and then 2, and then one possible remaining number. There's a formula for computing the maximum number of guesses for a set of size n consecutive values. The maximum number of guesses is the logarithm base 2 of n. Some of us never learned logarithms, and most of the rest of us have forgotten them. Let's just say it's the inverse function for exponentiation. The log base 2 of 100 is a little bit less than 7 because 2 to the 7th power is just a little bit greater than 100. This works with 128 as well. The logarithm base 2 of 128 is 7 because 2 to the 7th power is equal to 128. It turns out that the average case for guessing numbers between 1 and 100 is somewhere between 6 and 7. Because sometimes we will get lucky and guess the number before we get all the way down to one remaining choice. Now that we have a formula for the worst case number of guesses, we can apply the formula to problems of other sizes. How many guesses do you think it would take if we were guessing whole numbers between 1 and 1,000? It turns out that the answer is 10. The way we know this is that 2 raised to the 10th power is just a little bit bigger than 1,000. Let's demonstrate this. Starting with 1,000 numbers, our first guess would be either 500 or 501, either of which is near the middle of the list. We've divided the size of the problem set in half to only having 499 or 500 remaining numbers. We can keep on dividing the size of the problem in half in the same way. Half of 500 is 250. Half of 250 is 125. Half of 125 is somewhere around 62. I'll say 63. And half of that is 32. And so on, the remaining halves being 16, 8, 4, 2, and then our remaining guess must be the number. So the number of guesses is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, algorithm purists would say that this algorithm is ambiguous. When given the list of 1,000 numbers, how did we know whether to pick 500 or 501? Either is close to the middle of the list. It turns out that on average, it doesn't matter whether you have 500 or 501 elements in your list. You can keep on dividing it by 2 and getting similar results. In fact, we could have played this game up to 1024 because 2 to the 10th is 1024. And we could divide those in half and gotten 1024, 512, 256, 128, etc. Once again, the powers of 2. We can play the game with the numbers 1 through 1 million, too. How many times can you divide 1 million in half until your final guess must be the correct answer? We could compute the logarithm, base 2 of 1 million, or we could ask 2 to what power is greater than or equal to 1 million? I'll give you some time to compute that. It turns out that 2 to the 20th power is a little bit greater than 1 million. So it would take at most 20 guesses to find a number between 1 and 1 million. Don't believe this? The first guess would reduce the number of possibilities to 500,000. The second guess would reduce the number of possibilities down to 250,000. You can use your calculator to keep on dividing by 2 and see how many times it takes to get down to just one remaining number. If you don't like the inconvenient numbers that your calculator gives you, similar results can be achieved with this sequence: 500,000, 250,000, 125,000, 63,000, 32,000, 16,000, 8,000, 4,000, 2,000, 1,000, and we know that a number between 1 and 1,000 can be guessed in 10 guesses. So that was 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 more guesses, for a total of 20 guesses to guess a number between 1 and a million. Now, suppose you are Facebook. You have over 1 billion usernames. Let's say it's 2 billion just for round numbers. Let's suppose they are all sorted in alphabetical order. Someone wants to log in, so you need to find their password in your user database. If you use the binary search, the question arises, how many times can you divide 2 billion in half until you're left with only one possibility? Then guess that possibility. The answer is equivalent to 2 to the what power gives you a number greater than or equal to 2 billion. I'll give you some time to compute that. It turns out that 2 to the 31st power is a little bit larger than 2 billion. So if Facebook did a binary search on a sorted list of 2 billion usernames, they could find the user login information in at most 31 guesses. This is doable. If they used a linear search, the average number of tests would have been 1/2 of 2 billion, or 1 billion tests. That's a lot more work than the 31 tests used by the binary search. This is why we like the binary search, because it reduces the size of the problem quickly, so even very large problems become solvable in a reasonable amount of time. Now, a final note about the binary search. As we've described it, the algorithm is what is known as recursive. This means simply that we divide the problem into a similar problem of a smaller size and then apply the exact same algorithm on the smaller problem. We keep on doing this, dividing and reapplying the algorithm, until the problem becomes so small that the answer is obvious. In this case, until there's only one possibility left. I hope you have learned how the binary search works, and that it is much more efficient for a sorted list of values than a linear search. And we have seen that we can compare the best case, worst case, and average case performance of algorithms to choose the best one to solve a problem.